Irreducible tensor methods for molecular symmetry groups applied to icosahedral systems. Lawrence, it's always a pleasure to introduce you.
Thank you, Keith. I always put this title up because I figure out a number of years people will get used to it and won't be quite so frightening. Anytime you see the term tensor, it's a little spooky. This is actually in the category of mathematical chemistry, which is a subcategory of theoretical chemistry, which is a subcategory of physical chemistry, at least the way we do it here. Now, I want to show you, I'm going to summarize work that I've done over the years, but let's start at the basics, at the beginning. So I have been working with quantum mechanics, and the quantum mechanical calculation is defined by the Schrödinger equation and its state space. Symmetry corresponds to sets, usually groups, that commute with the Hamiltonian. So GH equals HG, and then what happens is that the state space becomes divided up into invariant subspaces and under the group, and then they're also going to be invariant to the Hamiltonian. Well, the result of that is that eigenvectors and eigenstates belong entirely to one of these invariant subspaces. And then this leads to the two basic purposes of group theory in quantum mechanics. The first one is the classification of eigenstates according to symmetry. This occurs because any eigenstate has to be completely in some symmetry state, and therefore all our job is to do is find out what it is. The other option is number two, and that is reducing the size of the matrices to be diagonalized because the subspaces are smaller than the big space. And that determines the size of the matrix that has to be diagonalized. The other one here is evaluating matrix elements of tensor operators useful for spectroscopy to come up with transition probabilities and things like that. Okay. Now, get a little mathematical here. Here I show you the decomposition of the vector space, the Hilbert space, and into its invariant subspaces under the group. And now the useful technique or tool for dealing with this is what we call a symmetry adapted basis. And these then are these cats that have these 1, 2, 3, 4 indices in them. You're beginning to see the tensor behavior. And we'll get a little more detail in a minute, but the point is that these transform irreducibly under the group. So if you have the suitably conditioned symmetry adapted basis, all of the elements will transform irreducibly under the group. The number of times the alpha irreducible representation occurs is given by this frequency, which is in fact calculated by the well-known established character formula. Now, if a defining basis of the state space is this one, for example, B omega, then a suitably conditioned symmetry adapted basis can be constructed using the primitive idempotent. And that is one of these right here, E alpha RS. They have various names, sometimes called Wigner operators, primitive idempotents, matrix basis elements, and so forth, but we're not going to spend too much time talking about their names. We're going to use them and show how, A, you construct them, and B, how do you use them as a projectors. I'm coming back to this later. I'm just giving you the overview at this point. Can you see okay? Okay.
These are just like the projectors in group theory.
That's correct. That's correct. If you notice at see this expression here? These are in fact linear combinations of group elements. They belong to, in fact, the algebra of the group. And these coefficients are the elements of irreducible representations. G here is the number of elements in the group, and F alpha is the size of the irreducible representation. So yes, you're right. Those are the ones. And
so what you've introduced here is just a new notation.
Well, it isn't new, it turns out. It's old, but this is an interesting question.
Yeah. If you go to like
right. They tend to, they like to use regular letters like L for the irreducible representation because that goes back then to Rocca's work on the atomic spectra. I'm using the ones that Weil and Littlewood used before Rocca. and so got stuck in it and stayed with it. But anybody who can transform Greek to Roman can make the conversion. Other questions? Okay. Well, since the Hamiltonian commutes with the group, it's going to commute with the elements of the algebra as well. And it turns out that its matrix elements are going to be diagonal over the alpha and the R indices, and they're going to be independent of the R index. The factor on the right, which is independent of the degeneracy index, is called the reduced matrix element because it's a smaller matrix and it's reduced. Makes it easier for us to get eigenvalues and eigenvectors. For example, a symmetric system, which in this case is cyclopropenyl radical. This has C3 symmetry because all three carbons are equivalent. Notice that just like in freshman chemistry, the symmetry of the molecule is determined by where the nuclei are, not where the electrons are. We have to keep reminding students of that. And, but if you then go to the symmetry adapted basis, this is an A1 invariant, then there are two E's here. You find that the expression becomes diagonal, and you have alpha plus 2 beta, and then you have alpha minus beta. So this, in fact, shows you the decomposition you see of the state space into two invariant spaces. It also shows you how you've reduced the matrix elements. This is a 2 by 2, and so on. So that's the easy one.
Mark,
Yes, sir.
is it C3 even though the two carbons
Well,
are to each other?
could even be C3V perhaps, or D3H. I would say this would be most likely D3H. But at least C3, because even D3H has a C3.
This doesn't seem like all sides are equal.
Oh, no, that's the point I was trying to make.
Yeah.
The point I'm trying to make is that it's not where the bonds are, which is where electrons are. It's where the nuclei are. It's where the carbon nuclei are. And so that you could draw, this is really one resonance structure.
So it's like with a benzene?
Yes, exactly, yes. Yeah, you could have those written, and
Oh, I didn't realize it had other resonance structures.
yeah. See, because all three carbons are the same, you can write two others. Not that this is a very common molecule, by the way. But other questions, okay. Okay, one of the things that I came up with over these years of rolling out papers is the symmetry generation theorem. And this has to do with using a molecule that you can construct by doing operations with a group. Now, for example, here, this molecule can be written as a summation over GR, where G is elements of the group, and the Hamiltonian can be written like this. And in that case, I say that it is symmetry generated because it's the symmetry group that's actually generating this whole molecule. You can visualize this if you had, let us say, a Buckminster fullerene, C60, and you can take one atom of that C60 and generate all the other 60s with 60 transformations. And I call that symmetry generation. Well, what that does is give us a handle on calculating reduced matrix elements. Because just because you have the matrix reduced doesn't mean you have the elements. And that may be tricky to get, or it may be easy. This certainly simplifies life a lot. If you have the reference Hamiltonian here and take its matrix elements over the symmetry adapted basis, then you can start, let's see, you can average over the diagonal terms, divide by alpha, multiply by n, and it'll give you reduced matrix elements, which is what you want. I will show you how this works with C60 in a little bit. In fact, I published the use of this with C60. But here's an example. I forgot I put this simpler one in. And you see, you have 1, 2, 3, and you do the transformations, add them up, and you get the nice symmetric case. And each of these you see is, in fact, a transformation. You can use HR. This can be your HR. And this is simply the identity times HR. Then if you use C3, what happens, the J goes down to the next step, and the K's get sorted. And then finally here, You add all those up and you get the original. So that's an example of symmetry generation. Is that clear? Okay. Okay, there's kind of a corollary, and this is the symmetry averaging corollary. Instead of multiplying by G, you divide by it. And so what this is you take a reference element like R, and it doesn't have the symmetry of the group, but if you transform it in some clever way, what you come up with is a system that has the symmetry. Now, it's not going to be the original reference group, but what can happen is now that you will have a reference compound, virtual compound, that has symmetry, and therefore you can apply the methods of group theory to this symmetric system. Then you want to go back to your original unsymmetric system. You can use perturbation theory or something like that. So this will give you help. I'm looking at, in fact, I have great hope and expectations of applying this to things like enzymes. What's your enzyme, Ricardo? The one that almost looks trigonal? Yeah, and of course they're not, but they're almost. And so perhaps one could, in fact, use this to come up with a actually virtual enzyme that was symmetric that you could do the calculations on, and then do perturbations to come up with the real. That's what I'm looking forward to. Ultimately, I like to be able to apply group theory to big, big, big systems. And I think we're going to have to someday. Symmetry averaging, when it does that, let's see, I've got these expressions in here. And so that just repeats what I said. Here's a nice pretty picture, color, Technicolor. And you see, I'm using this as a reference structure. And then if you just rotate it 120 degrees around, you end up with this. You have to average it. You have to divide by 3. And you come up with then our classic symmetric system. Now, this is a very simple case, but it gives us an idea of what we're talking about. And, okay, this, in fact, is a very simple case. I'm sorry, but these look pretty complicated, don't they? But the idea here is that we take the original reference system and transform it to a symmetry-adapted basis, and it becomes messier, okay? And then we want to come up with the reduced matrix elements. Well, those will be in the diagonal. Well, this one's right here is the lead-off term. That's the A1. So what will happen is that you have, this becomes equal then to A plus 2B when you've averaged it. And then here, to get these two, I have to add these two together, divide by 2, and then I will get A minus B. So I'll have A plus 2B, A minus B, and I now have the results that you saw earlier for the nice symmetric system, a same kind of a situation. So this is to try to help you get a handle on what we're doing. I hope I'm successful. Well, then H symmetric commutes with G, and the total Hamiltonian original is the sum of 2, and this is the start of a tensorial expansion of H, beginning with an invariant term. Now, whether this is computationally useful depends on how small H1 is to some extent. There's another way to get here, and I'm working on a paper, but that's another story. It's not done yet. Okay, the good old Wigner-Eckhart theorem. I hope that you will be able to remember this term, Wigner-Eckhart theorem, because like a lot of things in life, you will hear it. And then you'll be, you know, what in the world are you talking about? This is the Wigner-Eckhart theorem. It does apply to groups that are simply reducible. That means all coupling frequencies are 1 or 0. Then if that's the case, the matrix elements of irreducible tensorial sets, this T beta S, is proportional to a coupling coefficient and a reduced matrix element. The coupling coefficients can be tabulated. They're tabulated. You look them up, find them in books, on computers and things like that. This now you can say, okay, well, this is determined by the physics of the situation. And this can be very useful. Perhaps T beta is the dipole moment operator, and you're looking at transitions between two states. And you say, well, I wonder if I can get a transition between state alpha 1 and alpha 2. Well, you take a look at this coupling coefficient. If it's 0, it's forbidden. So this is the use of the Wigner-Eckhart theorem is a very powerful technique in trying to analyze spectra. Okay. Now, another thing, though, is to go a little bit further with it, and special operators can be defined, such as Rocker's unit tensor operators. Julio Rocca published a series of papers back in the 40s, early 40s, on the theory of atomic spectra. And they are difficult for people who know the area. They're challenging, but they're good, and they're very useful. And he really brought up a lot of ideas about what are called Lie groups. He was talking about the rotation group. And he laid the groundwork for, in fact, the kind of Lie group theory that's been applied ever since in elementary particles, where they've used different groups like SU3 and stuff like that. But he was using SU2, which you use for electrons and so forth. So Rocca laid the groundwork for that. It really did bug the physicists. They thought that group theory, they called them grouping pests, and really were hostile to people who wanted to use group theory. And it's interesting to go back, particularly in Germany, where most of this was. Okay, I came up with another one here called, I call it normalized irreducible tensorial operator. I should have used an N there. And I showed that when you do these, you come up with a set of matrices that are in fact complete for any particular space. This one right here, you come up and with these coupling coefficients in there, and you have 4 of these, right? And all 4 of these are independent, and you can express any 2x2 matrix in terms of these 4. And the interesting thing about it is the term that multiplies these, you see, transforms appropriately under the group. A1, A2, EE, and so forth. And so that is a neat trick that you can use that I was going to publish something. Here's an arbitrary 2x2 matrix, A, B, C, D, and you see how it works out. I haven't put down the math for it. The math is very simple and straightforward. Okay, let's go to the icosahedral group. Now, I'm sure everybody in here is familiar with the icosahedral group. Well, I could have brought a model of the buckyball, couldn't I? I have one in the room, but it's hidden over in the corner, and I didn't have room to bring it. But the group IH includes the inversion, and it has 120 elements. The 60 by 60 here, these are the proper rotations up in here, the character tables. Then you have 4 other quadrants depending on whether the inversion is involved in there. I'm not sure if you remember what an inversion is. Inversion is in fact reflection in the origin, so that x goes to minus x, y goes to minus y, and z goes to minus z. And what that does is take these proper rotations like C5, C5 squared, C3, and so forth, and converts them to improper rotations, and so forth. Okay, now the character tables for C20 and for C60 are right down here at the bottom. The characters of these, of the various operations. Notice what's interesting about these is C60, there's a 60 under the identity. Everything else is 0 until you come out here to this reflection, where there are 4. So if you're going to calculate the number of times an irreducible representation occurs, you know, in the 60 case, it's pretty easy because most of the terms are 0. Okay, if we're going to use the Wigner-Eckhart theorem or we're going to use the symmetry generation theorem, we need to have a handle on the direct products. Notice then that the thing that first hits us in the face is right here where there's a 2. There is a 2 here, and a 2 here, and a 2 here. That knocks this thing out as a simply reducible group. Sorry about that. The 32-point groups, just like point groups, are fine, not this. So the Wigner-Eckhart theorem, as we've grown to know and love it, won't apply here. We can fix things up a little bit. If it's only 2 terms, you can have 2 reduced matrix elements and 2 coupling coefficients. But this is going to require generalization, and if any of you students want to work on it, that's fine with me. I haven't decided that I really want to spend much time on it at this point. For one thing, everything with an A in it is 1. So if you're going to do the symmetry generation or the averaging, which is basically projecting to A, you're cool. There's no problem. But it's just the ones that would involve these others. All righty, here is C60. Does it look like C60? It's called a Schlegel diagram. It's very good, actually. And you can see here that see, this is carbon 1 here, carbon 2, carbon 5, and carbon 7. Carbon 1 is bonded to carbon 7, carbon 5, and carbon 2. Notice that the 1,5 bond and the 1,2 bond are in the pentagon here, and that the 1,7 bond is an edge of a hexagon. The C60 has 2 kinds of bonds. The kind that are in the pentagons, the kind that are in the hexagons. But that's not going to stop us. I have here a couple of generators for the group indicated. A C2 group has an axis from here to here. There's another one, C5, you see, would be around in the middle of this pentagon. Okay. Well, here's your reference. Now, that's a lot nicer looking than it's a 60 by 60 matrix, but it's mostly zeros. And you just have one alpha there for that number 1 carbon. I'm going to do simple Hucol theory, which is okay, by the way, in case you wondered, especially if you're doing mathematical chemistry. And you see here, then these are the 1, 2, beta, 1, 2, 3, 4, 5, and then 7 over here. The 7 has a beta prime because it's a different bond from the others. You have to divide by 2 because when you add them up, you know, if you didn't divide by 2, you double it. That's all that matters. Okay, so let's do it. Wow. Okay, this is working all the way to the end. And what are these things? These are matrix elements of the Z1. This is the beta matrix elements. This then is the reduced matrix element. According to the theorem that I pronounced, to get these, you have to sum these up, average these, and multiply by 60. Because I was using 60 terms in the generation. Notice that if I take 0.0333 times 60, I get 2. Well, that's nice. So the term is 2 beta. All this work to come up with just 2 beta. You should be impressed. But the fact is, it was done by a computer, see? So while it could be done by hand, and actually has been, I think, by some Chinese, you're not going to have mistakes here with a computer, which is nice. And then the same way here, you add these 3 terms up, again, multiply by 60, you get this one, and so forth down the line. These are the correct reduced matrix elements. I do point out here that the G is repeated, 1, 2. H, G is, let's see, it's 3 times. And T1 is twice, T2 is twice, and so forth. Notice that you have nice -1s and zeros up these for these things. And the result comes out very nicely. I actually, in the paper I published, I actually did a plot of the energy levels versus the ratio beta over beta prime, and found the optimum intersection and compared that with the experiment, and it worked out really nice. Now, how are we doing? Pretty good. I was going to do 40 minutes. Isn't that what you said? 40 minutes. Okay, well, let's go back to this problem of symmetry adapting, getting a symmetry adapted basis. That is not a trivial problem. And that's what I'm going to talk about now. I'm going to finish up with all of this. And okay, our initial Hilbert space or state space will be V omega. These are familiar. The state space is going to transform under the symmetry group in this way, some matrix. Presumably, I can get my hands on it. And also, presumably, if I'm smart, I've got it for generators and generating relations, so I can have the computer generate all of these matrices, which is what I did. Okay, let's look at these. Are Dr. Eastman's favorite operators, the ones you asked me about. And you can see that they have certain properties I want to emphasize. Assuming it's a unitary group, then E alpha RS is the Hermitian adjoint E alpha SR. Okay, they are orthogonal. If you multiply them together from different alpha and beta, you get 0. And a different S and T, you also get 0. And then you end up with E alpha RU. Now, this actually is related to the great orthogonality relations in group theory. Notice that if you take this one, where you used 1, 1, 1, 1, is simply, this is idempotent. I'm not sure how familiar you are with that word. Idempotent means multiply it by itself and get it again. Everybody knows at least 1 or 2 idempotents, right? 1 times 1 is 1. 0 times 0 is 0. But here are some others that are not 1, for example. And in fact, it's important that they not be 1. And then they transform irreducibly under the group right here. Okay, that's an irreducible representation. So now what? Well, I want to project from the original basis with this, and that means I've got to know how the original basis transforms under these. Well, I plug in the expression that we had, and you can see then that the transformation is going to be a sum now over these GA matrices. This is how we calculate these, and it's fairly straightforward for a computer. People are getting restless. Don't surprise me, because there are an awful lot of terms here. But now, when we get eigenfunctions to E alpha 1, 1, we've got to get rho F omega alpha of those, because that's the number of times that they repeat. And so rho is the one that indexes them, and so we've got to find this many. If we do find this many, then all the rest are simply obtained by these operators. And so basically, this is the big job. Once we got that, this follows pretty quickly. Okay. Well, there's a problem. I want to solve for the eigenvectors of E alpha 1, 1. But there's a lot of degeneracy, or at least some degeneracy, because I've got a lot of 1s and 0s. The eigenvalues of E alpha 1, 1 are 1 and 0. And that means that if I'm going to try to get eigenvectors, I've got a problem making sure that they are not close to dependent. They need to be substantially linearly independent. So, what I published, and which seemed to make Dieter Kramer very excited, is to use the properties of this matrix, the Hermitian idempotent property of this matrix. Notice that if I multiply it by itself, I get it back, don't I? So this is multiplying 2 matrices together to get the original matrix. But hey, now it's I can do this is a Hermitian matrix. I can simply star this and switch the indices, and now what I've got really is a sum over J. I've got, in fact, the inner product of two columns here, two vectors. This is a dot product between 2 vectors in this matrix. And this means that this is, in fact, the value of the inner product. This matrix element is the Hermitian inner product of the ith and kth columns of this original matrix, while this one is the norm squared. All we have to do is assemble F omega alpha columns with the largest determinant of the inner product matrix. That makes it independent. This will be this set when I get it, okay? Now, can the computer do this? Yes, the computer can do this. If it's a big set, you want to use a computer for it. If it's only 2 or 3, maybe not. But now, this will get us where we want to be, which is the symmetry-adapted basis. Okay, last slide. This is an 8 by 8 upper quadrant of the matrix of E alpha R1, 1, from benzene. And these are the kind of numbers that you get out of the computer. Actually, they've been multiplied, I think, by 120 to get them to be more readable. Otherwise, they're kind of small. And you go down here and say, hey, look at that. That's 10. I think I'm going to pick that one to be my starting vector, so I'll put it right here. And then I go down where? Well, that one's pretty big, too. Let's put it next. And then let's see. Well, there's another 10 down here somewhere, but you know what? If I'm not careful, that one might be the same as the original, but it turns out not to be. And so I take the determinant of this, get 392.705. If I really want to get the numbers, I multiply by 120 cubed, and it all works out real sweet. This is how one comes up with a symmetry-adaptive basis. And that's what Dieter wants me to give him. He wants to do it on vibrational states of buckyball. And because he says it's just too much by hand. And so I promised him I'd help. So this really completes the presentation today. I'll be happy to answer any questions.